Hello there, and welcome. Tonight I want to take you somewhere far beyond the ordinary boundaries of your everyday awareness, into a realm where questions outnumber answers and where the greatest mysteries of existence unfold in profound silence. I want to invite you to journey with me through the cosmic darkness, to contemplate something so fundamental, so utterly pervasive, yet so completely invisible that it challenges everything we think we know about the universe itself. But before we begin this gentle exploration together, I want to know that you're with me on this journey. If you find yourself captivated by the wonder of the cosmos, by the profound questions that make us gaze upward at night and feel both infinitely small and deeply connected, then please like this video and subscribe to our channel. Your support helps us continue these contemplative journeys into the mysteries that surround us. And I'd love to know where you're watching from right now. Are you settling into bed somewhere warm and safe? Are you in a quiet room where the world feels distant? Please tell us in the comments where you are and what time it is where you are, because even though we might be separated by vast distances across this planet, we're all looking up at the same sky, all wondering about the same cosmic mysteries. We're all part of the same universe, contemplating our place within it together. Now, imagine for a moment that the vast majority of everything, the very substance that holds galaxies together, that shapes the structure of all creation, that gravitationally orchestrates the cosmic dance of billions of stars and planets, imagine that this majority of existence is completely, utterly invisible to us. It's a question that might initially feel like the stuff of science fiction or philosophical speculation, but it challenges our fundamental understanding of reality in ways both humbling and wonderful. Yet what if I told you that this invisible substance is not a mystery waiting to be solved with the right telescope, not something that will suddenly reveal itself when we build a more powerful instrument, but rather something whose very nature, the fundamental reason it doesn't interact with light at all, has profound and beautiful implications for how we understand the universe? What if the reason dark matter doesn't reflect any light is not because we haven't found the right way to look, but because it exists on a different level of reality entirely, interacting with the cosmos through the language of gravity alone, speaking only to those who understand the silent music of the universe's deepest structures? This is the journey we're about to undertake together, a contemplative exploration of dark matter, that cosmic ghost that fills nearly 85% of all matter in the universe, yet remains forever hidden from the electromagnetic radiation that makes everything we can see possible. We'll wander through the discoveries that reveal this mystery through the scientific observations that whisper to us about its presence, and through the implications that gently reshape how we understand our own significance in a universe mostly made of things we cannot touch, cannot see, and cannot directly perceive. But this journey is not one of alarm or urgency. Rather, it's an invitation to drift through cosmic wonderland at your own pace, to let your mind relax into the profound questions that have occupied humanity's greatest thinkers, and to find peace in the realization that the universe is far more mysterious, far more beautiful, and far more connected than we often imagine. As we settle into this exploration, I want you to imagine yourself lying somewhere comfortable, perhaps looking up at a ceiling that, in your mind's eye, becomes the vast night sky itself. Around you, even now, in this very moment, dark matter passes through your body, through the earth, through everything. It doesn't touch you in any physical way that you can feel, yet it's there, billions upon billions of particles, moving silently through space, interacting only through gravity with the things we can see. You are in this moment surrounded by the universe's greatest mystery, floating within an ocean of invisible substance that your mind is beginning to comprehend, even as your body prepares to drift towards sleep. The wonder of this realization, that we exist within something so vast and so completely hidden, is perhaps the perfect doorway into the contemplation that will carry you gently into your dreams. The story of dark matter begins, as so many cosmic stories do, with a puzzle. In the 1933, a Swiss astronomer named Fritz Zwicky was observing clusters of galaxies through his telescope, watching how they moved through space, how they interacted with one another through gravity's invisible pull. He was attempting something that seems simple now but was revolutionary then. He was trying to weigh the universe. By observing how galaxies moved within clusters, By studying their velocities and their gravitational interactions, he could calculate how much mass must be present to hold these cosmic communities together. But something didn't add up. The galaxies were moving too fast. By all the calculations that seemed solid and trustworthy, these galactic clusters should have flown apart like a group of birds suddenly released from a cage, their gravitational connections far too weak to hold them together against their own momentum. Yet they remained bound, clustered together as if held by invisible hands, as if there were far more matter present than what he could actually see and measure through his telescopes. Zwicky called this mysterious invisible matter dunkle Materie, dark matter, and for decades his observation remained largely overlooked, a curious anomaly in astronomical data rather than a fundamental revelation about the universe. Scientists continued with their work, observing the cosmos through traditional means, confident that the matter they could see, stars, galaxies, interstellar gas, dust, accounted for most of what was out there. But then, in the 1973, an American astronomer named Vera Rubin, working with fellow astronomer Kent Ford, made an observation that would ultimately force the scientific community to confront Zwicky's decades-old mystery. They were studying the rotation of individual galaxies, watching how stars at different distances from a galaxy's center moved through space. What they found was profoundly strange. According to everything physicists and astronomers believed about gravity and orbital mechanics, stars farther from a galaxy's center should move more slowly, just as planets farther from the sun move more slowly in their orbits. The mathematics was clear, the physics was understood. But what Rubin and Ford observed was something different entirely. Stars at the edges of galaxies, far from their centers, were moving just as fast as stars closer in. It was as if the galaxies were surrounded by enormous halos of invisible matter, massive clouds of dark stuff that couldn't be seen, but whose gravitational presence explained why the outer stars didn't slow down as they should. Suddenly, Zwicky's observation from decades before made sense. Suddenly, the universe looked dramatically different than anyone had imagined. If galaxies were surrounded by these massive halos of dark matter, if dark matter vastly outnumbered the visible matter that made up all the stars and planets we could see, then our entire understanding of what the universe was made of needed to be completely reconsidered. The visible universe, the stars, galaxies, nebulae, all the magnificent structures we could photograph and study and marvel at, was not the universe itself. It was merely the glowing surface of something far deeper, far more extensive, far more mysterious. It was like discovering that the vast majority of an iceberg was hidden not beneath the water, but existing in a completely different state, in a different dimension of reality that we could only perceive through its gravitational effects. This realization sent ripples through the scientific community, and since Rubin's observations in the 1970s, astronomers and physicists have worked tirelessly to understand this cosmic mystery. They've developed increasingly sophisticated instruments to detect dark matter indirectly, to map its distribution throughout the universe, to understand how it shapes the very structure of galaxies and galaxy clusters. Space telescopes like the Hubble Space Telescope have observed the effects of dark matter, bending light from distant galaxies through a phenomenon called gravitational lensing, where massive amounts of dark matter warp space itself, distorting the light that passes through it like a lens made of glass. The Chandra X-ray Observatory has mapped the distribution of dark matter in galaxy clusters by observing hot gas, which tends to follow dark matter's distribution. The European Space Agency's Planck satellite has measured the universe's cosmic microwave background, the ancient light left over from the Big Bang itself, with such precision that it can tell us with remarkable accuracy how much dark matter the universe contains. And all of these observations, all of this accumulated evidence, points to the same stunning conclusion. Dark matter makes up about 85% of all the matter in the universe. Visible matter, everything we can see, everything we can touch, everything we've ever known to exist, comprises only about 15% of the total matter content of the cosmos. Pause for a moment and let that sink in. Everything in your life, everything in human history, every discovery science has ever made, every moment of wonder humans have ever experienced gazing at the night sky, all of it has been about the 15%. The stars that guided ancient navigators across oceans, the sun that warmed the earth and made life possible, the atoms that make up your body, the light itself that carries information from the most distant galaxies. All of this glorious, complex, beautiful, visible universe comprises only 15% of the matter in existence. The other 85%, the vast majority of the universe's substance, remains mysterious, remains invisible, remains beyond our direct perception. If you're still watching with us, if this realization has captured your attention, if you're beginning to feel the profound wonder of this cosmic mystery, please pause for a moment and let us know in the comments. Tell us what aspect of this dark matter mystery fascinates you most. Is it the sheer scale of it? Is it the mystery of its nature? Is it the realization that we live in a universe mostly made of something we can't see? Your comments help us understand what aspects of these cosmic journeys touch your hearts and minds most deeply. Now, you might wonder, and this is a profoundly natural question to ask, if dark matter is everywhere, if it's the dominant form of matter in the universe, why have we only discovered it in the last century? Why didn't ancient astronomers notice its presence? Why didn't we see it sooner? The answer lies in something beautiful about how science works, something that speaks to both the limitations and the powers of human observation. Dark matter doesn't announce itself through light. It doesn't shine. It doesn't glow. It doesn't reflect starlight or emit radiation that our telescopes can detect. For millennia, humanity's window on the universe was light. The visible light from stars, the infrared radiation from warm objects, the ultraviolet light from hot stars, the radio waves from distant sources, the X-rays from energetic phenomena. All of these are forms of electromagnetic radiation, part of the spectrum of light in its various forms. And dark matter, by its very nature, doesn't interact with electromagnetic radiation in any way that allows it to be seen, to be illuminated, to be made visible to our instruments. It is, in the truest sense of the word, dark. Not dark because it's opaque and absorbs light, but dark because it doesn't interact with light at all. This is a fundamentally important distinction, and it shapes everything about how we study dark matter and why it remained hidden from us for so long. When we see a dark cloud in space, we're seeing dust particles that absorb starlight and appear dark against the background sky. But dark matter doesn't work that way. It doesn't absorb light, doesn't reflect light, doesn't interact with light in any way. It exists in a sort of cosmic invisibility, detectable only through the gravitational influence it exerts on everything around it. This means that for billions of years, dark matter shaped the structure of the universe, guided the formation of galaxies, held clusters of galaxies together, and quietly conducted the cosmic symphony, all while remaining utterly, completely undetectable through any method that involved looking at light. Humanity needed to learn to see with different eyes, to develop new ways of understanding the universe that didn't rely on the electromagnetic spectrum. We needed to learn to read the language of gravity, to see the world through the invisible architecture of space-time itself, and this is where the story becomes truly profound. In developing the mathematics of gravity, in understanding how massive objects curve space and time around them, Albert Einstein gave us the tools we needed to eventually perceive dark matter. Einstein's theory of general relativity, published in 1916, described gravity not as a force in the Newtonian sense, but as a warping of the fabric of space-time itself. Massive objects tell space how to curve, and curved space tells objects how to move. This elegant description of gravity means that if something is massive, if it has gravitational presence, then it will affect the curvature of space-time around it, and anything moving through that space will respond to that curvature. It doesn't matter whether the massive object produces light or not. It doesn't matter whether we can see it. Its gravitational presence, its curvature of space-time is real, is measurable, is detectable through its effects on other objects. This insight, coupled with the development of increasingly sophisticated telescopes and observational methods, eventually allowed Zwicky and then Rubin to detect dark matter not directly, but through its gravitational signature. They observed how galaxies moved, how their velocities didn't match predictions based on visible matter alone, and from this discrepancy, they inferred the presence of something invisible, yet massive. It was a bit like hearing wind and inferring the presence of air, like seeing ripples on water and understanding that something beneath the surface had disturbed it. The universe, it turned out, was far more complex, far more layered, far more mysterious than anyone had imagined. And the discovery was only the beginning of our journey toward understanding what dark matter actually is. As you rest with us in this contemplation of cosmic mysteries, consider how remarkable it is that dark matter has been present throughout all of human history, shaping the universe's structure, governing the motions of galaxies, yet remaining invisible until our species developed the mathematical and observational tools necessary to perceive it. It suggests something profound about the nature of reality, that what we can see is not the whole story, that mystery can be woven into the very fabric of existence, and that our expanding understanding of the universe is itself a kind of cosmic awakening. The universe has always been this way, always been mostly dark matter, always been far more subtle and mysterious than appearances suggest. We're only now beginning to truly see it. The observations that revealed dark matter's existence came from studying how gravity worked on cosmic scales. Zwicky noticed that galaxy clusters moved in ways that gravitational attraction alone, based on the visible matter, couldn't explain. Rubin noticed that galaxy rotation curves didn't match theoretical predictions. But what was actually happening was that light from distant galaxies, as it traveled across billions of light-years of space, was being bent and distorted by the gravitational fields of massive structures it passed through. When Einstein developed his equations of general relativity, he predicted that massive objects would bend light, and this prediction was confirmed during a solar eclipse in 1919, when astronomers observed starlight bending around the massive sun. But light bending around dark matter, around structures invisible to every telescope designed to detect electromagnetic radiation, would take much longer to observe and understand. It wasn't until the 1980s and 90s that astronomers like Jim Peebles and others developed the theoretical framework to understand how dark matter could be detected through the lensing of light from distant galaxies. Imagine a distant galaxy so far away that its light has been traveling through space for billions of years to reach us. Now imagine that this light, on its journey to Earth, passes through or near a massive concentration of dark matter, perhaps surrounding a galaxy cluster, perhaps in some other cosmic structure. The dark matter's gravity doesn't just subtly influence the light's path, it actually bends it, focuses it, distorts it, much like a giant lens made of glass might bend light rays passing through it. When astronomers look at distant galaxies, they sometimes see them distorted or even split into multiple images, as if the galaxy's light has been bent around an invisible lens. By studying these distortions, by mapping how light is bent as it passes through space, astronomers can create maps of where dark matter is located, even though they cannot see it directly. They are, in essence, reading the universe's structure through the way it bends light, through gravity's signature written across the cosmic distance. This method, called gravitational lensing, became one of the most powerful tools for studying dark matter. The Hubble Space Telescope has used it to map dark matter in galaxy clusters, revealing that dark matter isn't distributed evenly, but rather concentrated in certain regions, creating cosmic structures that guide the formation and distribution of visible galaxies. The lensing maps look like beautiful, intricate patterns, not unlike the rings around a stone dropped in water, except these are three-dimensional patterns extending billions of light-years into space, sculpted by the invisible gravity of dark matter. And perhaps most remarkably, the patterns revealed by lensing maps match perfectly with what astronomers predict dark matter's distribution should be based on other observations. The evidence accumulates, layer upon layer, pointing always toward the same profound conclusion. The universe is filled with dark matter, and we're learning to see it not through light, but through understanding gravity's effects. The realization that we live in a universe so dramatically different from what we can see has profound implications. It means that the night sky, beautiful and mysterious as it appears to our eyes, is merely the glowing surface of something far vaster and more intricate. It means that when we look up at the stars and feel that sense of infinite wonder, that sense of standing before something far larger than ourselves, we're only perceiving a small fraction of what's actually there. Around every visible galaxy, extending far beyond the galaxy's glowing disk of stars, is an enormous halo of dark matter, invisible but massive, shaping the galaxy's structure and motion. The stars we see are, in a sense, jewels set into a much larger framework of darkness. brilliant points of light suspended in an ocean of invisible substance. The beauty of this realization is that it doesn't diminish the wonder we feel when gazing at the night sky. Rather, it deepens it immensely. It suggests that there is far more to the universe than meets the eye, that reality is more subtle, more complex and more mysterious than any of us imagined. As we continue our exploration, remember that you are yourself made of visible matter, made of atoms forged in the hearts of stars, made of the very substance that comprises only 15% of the universe's matter content. Yet within your own body, dark matter is passing through constantly, billions of dark matter particles moving through every atom, every cell, every thought you're thinking right now. You are quite literally nested within dark matter, surrounded by it, connected to it through gravity's ancient threads. This isn't something to fear or find unsettling. Rather, it's something to contemplate with wonder, the realization that you, a being made of visible matter, conscious and aware, exist within a universe where the vast majority of substance is invisible, where mystery is woven into the very fabric of existence, where questions perpetually outnumber answers. The discovery of dark matter transformed astronomy from a science that studied visible light to a science that reads the universe's deeper structures through gravity, through the bending of light, through cosmic patterns too vast for any individual to fully comprehend. It forced scientists to acknowledge that their instruments, no matter how powerful, could only detect a small fraction of what actually exists. It humbled the scientific community in the most beautiful way by revealing how much more there was to learn, how much more was hidden, how vast the unknown truly is. And this brings us to one of the most profound questions we can ask. If dark matter comprises 85% of the universe's matter, why doesn't it reflect any light? What is its nature? What fundamental properties make it so completely invisible to every form of electromagnetic radiation? These are the questions that have occupied physicists and astronomers for decades, the mysteries that continue to drive scientific research and cosmic exploration. And as you drift deeper into contemplation, as your mind begins to relax into these profound thoughts, as your body settles into the comfort of rest, consider this: the very nature of dark matter, its invisibility, its subtlety, its presence known only through effects, mirrors something about consciousness itself, about awareness, about the way we perceive reality. What we see is not the whole story. What we can measure directly is only part of the truth. Beyond the visible, beyond the measurable, lies mystery. And mystery, perhaps, is not something to be feared, but something to be contemplated with gratitude and wonder. The question that puzzled physicists and astronomers for so long had a surface answer and a deeper answer. The surface answer was simple. Dark matter doesn't reflect light because it doesn't interact with electromagnetic radiation. But what did that really mean? To understand this profoundly, we need to contemplate what light actually is and how matter typically interacts with it. Light, as we understand it now, is a form of electromagnetic radiation. Ripples in the electromagnetic field that travels through space at a constant speed, the speed of light, carrying energy and information from place to place. When light encounters ordinary matter, a piece of glass, a human face, a leaf on a tree, something happens. The light either passes through the matter, bounces off it, or is absorbed by it. These interactions, transmission, reflection, and absorption, are the only ways we see anything at all. Light bounces off the sun's face and travels to our eyes, allowing us to see the sun. Light reflects off a white surface and carries information about its color to our eyes. Light is absorbed by a black object, which is why black objects appear dark. But in every case, light is interacting with the object, and this interaction is what makes the object visible. This interaction between light and matter happens because atoms and molecules have electrons, and electrons interact with the electromagnetic field of which light is composed. When a photon of light encounters an electron, the photon can be absorbed, causing the electron to jump to a higher energy level. The electron then quickly decays back to its original level, releasing the photon again. This process happens countless times as light passes through matter, and it's what gives matter its color, its transparency or opacity, its ability to be seen. But dark matter, as far as we can tell, has no electrons in the traditional sense, no charged particles that interact with electromagnetic radiation. It seems to be made of particles that simply don't have an electrical charge and don't interact with photons, the particles of light, in any way at all. The dark matter particles pass through light, and light passes through dark matter, and neither is affected. They are in the most fundamental sense invisible to each other. Now this might sound strange or impossible, but consider that it's actually quite elegant from a physics perspective. The universe contains 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Ordinary matter, the stuff you're made of, the stuff stars are made of, the stuff of everything we can see, interacts through all 4 of these forces, but dark matter appears to interact only through gravity. It doesn't interact through electromagnetism, which is why it doesn't interact with light. It doesn't seem to interact through the strong nuclear force, which is why it doesn't form nuclei or atoms. And while it might interact through the weak nuclear force, we haven't detected such interactions yet. Dark matter is, in essence, the universe's most introverted substance. It interacts with the cosmos only through the gentlest force, gravity, which is the weakest of all forces on individual particle scales but the strongest on cosmic scales because gravity is always attractive, never repulsive, and affects all mass equally. This distinction is crucial to understanding why dark matter doesn't reflect any light. Reflection, in its essence, is what happens when light interacts with charged particles in matter. The light, a photon, encounters an electron, exchanges energy with it, and bounces away in a different direction. The light doesn't pass through unchanged. It's deflected, redirected, sent back toward its source or in some new direction. This is why we can see reflections. Light bounces off surfaces and carries those reflections to our eyes. But for light to be reflected, it must interact with something that can interact with electromagnetic radiation. Dark matter particles, whatever they are, don't have this property. A photon of light passes through a cloud of dark matter particles as if the cloud weren't even there. The photon continues on its way, undeflected, unchanged. No light bounces back, no reflection occurs, no image forms. The dark matter remains invisible, not because it's hidden behind something, not because it's in shadow, but because it fundamentally doesn't interact with the thing we use to see, light itself. This is why dark matter is so profoundly different from ordinary dark objects. If you covered something opaque with a black cloth, the cloth would still interact with light. It would absorb the light, preventing it from reaching whatever is beneath. The cloth would be visible as a dark silhouette against a lighter background because it blocks the light that's behind it. But dark matter doesn't block light. Light passes right through it. A region of space filled with dark matter would appear completely empty to any telescope or instrument designed to detect light, because dark matter is literally transparent to every form of electromagnetic radiation. You could point the most powerful telescope ever built at a region of space containing trillions of dark matter particles, and you would see nothing. You would see right through them as if they weren't there. Yet if you could measure gravity in that region, you'd find it incredibly strong. You detect the presence of enormous mass. You'd see evidence of the dark matter's presence through its gravitational effects. This transparency of dark matter to light is, when you think about it philosophically, one of the most profound characteristics of the universe. It suggests that the universe has multiple layers of reality, a visible layer made of light-interacting matter, and an invisible layer made of matter that only gravity can detect. These layers overlap, they coexist, they interact only through gravity, yet they never see each other in the way visible matter can see visible matter. An atom in your body will never see a dark matter particle. The dark matter particles passing through your body right now will never interact with you except through gravity. You and the dark matter are like two inhabitants of the same space, yet completely unaware of each other except for a gentle gravitational tug that you would never perceive. Scientists have long speculated about what dark matter might actually be made of. The leading candidates are things called weakly interacting massive particles, or WIMPs, and tiny rotating particles called axions. WIMPs are hypothetical particles that would have mass, but interact with ordinary matter only through gravity, and perhaps the weak nuclear force, not through electromagnetism. They would be affected by gravity and by other WIMPs' gravity. but they would pass through ordinary matter and light without interaction. Axions, on the other hand, are predicted particles arising from certain theoretical extensions of the standard model of particle physics. They would be incredibly tiny, far smaller than electrons, moving at relativistic speeds through the universe in vast numbers, creating a background ocean of axion particles permeating all of space. Both of these particle types would have one crucial property in common. They would not interact with electromagnetic radiation, neither would reflect light, neither would absorb light, neither would emit light. They would be completely invisible to every telescope, every instrument, every photon detector that humans have ever created. The beautiful mystery of dark matter's invisibility to light points to something deeper about how we understand the universe. For most of human history, our understanding of reality was limited to what we could see. We assumed that what was visible was all that existed, that the universe was essentially what it appeared to be when we looked up at the night sky. But as scientific instruments became more sophisticated, as our understanding of physics deepened, we began to realize that visible light was just one small window into a much vaster reality. In the last century, we've learned that there's invisible infrared radiation carrying heat, invisible ultraviolet radiation that can damage our skin, invisible radio waves carrying information across the world, invisible X-rays from the hottest objects in the universe, invisible gamma rays from cosmic explosions. The electromagnetic spectrum extends far beyond the narrow range of visible light that human eyes can see. Yet even all of this vast spectrum of radiation passes through dark matter as if it weren't there. This revelation, that the majority of the universe is completely invisible to every form of electromagnetic radiation, suggests something profound about the nature of reality and our perception of it. It tells us that the universe is far more subtle, far more intricate, far more mysterious than any previous generation of humans could have imagined. It tells us that if we ever encounter other forms of life or intelligence in the cosmos, they might have completely different ways of perceiving reality, ways that don't rely on detecting light or any form of electromagnetic radiation. Perhaps some hypothetical cosmic intelligence might perceive the universe primarily through gravity, through the subtle warping of space-time, seeing dark matter as clearly as we see visible galaxies. The very invisibility of dark matter to light suggests that light, and the electromagnetic spectrum more broadly, is perhaps not the fundamental language of the universe, but merely one dialect among many. Consider for a moment what it would be like to be a dark matter particle drifting through space. You would never experience light, never see the glow of distant stars, never witness the brilliance of a galaxy. You would perceive the universe only through gravity's gentle pulls and pushes, feeling the presence of other particles around you only through their gravitational attraction. You would move silently through the cosmos, passing through galaxies of visible matter, being unaware of their existence except for the gravitational disturbance they create in your path. You would experience the universe in a way completely alien to how humans experience it, yet you would be part of the same cosmos, connected to everything else through gravity's ancient threads. It's a beautiful thought, isn't it? That the universe contains forms of matter, experiencing reality in ways so fundamentally different from how we experience it, yet always connected, always gravitationally intertwined, always part of the same grand cosmic whole. The reason dark matter doesn't reflect any light, then, is not a mystery waiting to be explained by discovering some special property of dark matter. Rather, it's simply the consequence of dark matter's fundamental nature as matter that doesn't interact with electromagnetic radiation. It's matter that exists in the universe following the rules of gravity alone, then indifferent to the light that illuminates everything we can see. And this very indifference, this complete non-interaction with electromagnetic radiation, is perhaps the key to understanding dark matter's role in the universe. Because dark matter doesn't interact with light, it also doesn't interact with the radiation pressure that light can exert. Radiation pressure is the subtle pushing force that light exerts on matter, and it has profound effects on how visible matter behaves in the universe. Radiation pressure from stars can push gas away, can shape the formation of galaxies, can drive cosmic winds. But dark matter is unaffected by this pressure. It gathers and clusters under gravity's influence alone, forming the cosmic scaffolding upon which galaxies are built. This means that dark matter and visible matter follow slightly different rules in the universe. Visible matter is buffeted by radiation, shaped by the light from stars, affected by electromagnetic forces in countless ways. But dark matter follows a simpler set of rules, gravity and nothing else. In a sense, dark matter is the universe's most fundamental substance, following only the most fundamental force. Visible matter is more complex, more interactive, more chaotic. Yet visible matter, the stars and galaxies and atoms, is what creates light, and without light, without visible matter, dark matter would remain forever unknown to us. We see the universe through the light of visible matter, and through understanding that visible matter's behavior, we infer the presence of the invisible dark matter that surrounds it. The two are locked together in a cosmic dance, dark matter providing the gravitational structure, visible matter providing the light through which we perceive that structure. As you rest and contemplate these ideas, as you let your mind drift through the cosmic spaces we're exploring together, consider the profound beauty in this arrangement. The universe is not what it appears to be. What we see is real and wonderful. The galaxies, the stars, the intricate cosmic structures revealed to us through telescopes and observations. But what we see is built upon, supported by, embedded within a vaster substrate of dark matter that we cannot see, cannot touch, cannot perceive except through gravity's patient revelation. It's like discovering that the universe has depth, that reality has layers, that beneath the visible surface lies an infinite ocean of invisible substance, and the fact that this invisible substance doesn't reflect any light, the fact that it remains forever dark to every photon, every radiation detector, every instrument we could ever build, is not a problem to be solved or a limitation to be overcome. It's simply the nature of dark matter, the fundamental property that makes it what it is. This invisibility to light, this fundamental non-interaction with electromagnetic radiation, becomes even more remarkable when we consider what it means for how dark matter distributes itself throughout the universe. Unlike visible matter, which is shaped by radiation pressure, by the push and pull of stellar winds, by the electromagnetic forces that govern chemistry and atomic structure, dark matter follows a path determined solely by gravity. It collects where gravity is strongest, it flows along the geodesics of curved space-time, it responds only to the presence of mass around it. And because dark matter is so abundant, because it comprises 85% of all matter, it essentially sets the gravitational stage upon which the drama of visible matter unfolds. The galaxies we see, the cosmic structures that we observe with our telescopes, are arranged not primarily by the distribution of visible matter itself, but by the underlying cosmic web of dark matter that surrounds and supports them. It's as if the visible universe is a magnificent tapestry woven upon a loom made entirely of invisible threads. This brings us to one of the most profound discoveries of modern cosmology, the realization that galaxies don't form randomly scattered through space, but rather along filaments of dark matter that extend across billions of light years. These filaments, these cosmic highways of dark matter, guide the formation and distribution of galaxies throughout the universe. A galaxy is born not in isolation, but at the intersection of these dark matter filaments, in regions where dark matter has accumulated under gravity's pull. The visible matter, the gas and dust that will eventually form stars, collects in these regions, drawn inward by the dark matter's gravity, condensing and heating until stars ignite. This means that every galaxy you've ever seen, every brilliant spiral or majestic elliptical galaxy captured in photographs from the Hubble Space Telescope, exists because of dark matter's invisible architecture. The visible galaxies are, in a very real sense, ornaments hung on the framework of dark matter. Consider what this means for our understanding of cosmic structure. For millions of years, astronomers built mental models of the universe based on what they could see: the galaxies, the stars, the nebulae. They drew maps of the universe by counting and cataloguing visible objects. But these maps were incomplete. They were like looking at a forest at night with only a flashlight, seeing individual trees illuminated by the beam, but remaining ignorant of the vast forest surrounding the beam's reach. The dark matter filaments that structure the universe, that guide galaxy formation, that hold cosmic structures together, these remained invisible, undetected, unknown. It wasn't until scientists developed theoretical models based on gravity and observations of how galaxies actually distribute themselves in space that they realized an invisible scaffolding of dark matter must exist. And now, through sophisticated computer simulations and observations of gravitational lensing, astronomers can map this dark matter structure, can visualize the cosmic web of dark matter filaments that shape the universe's architecture. The implications of this realization are profound. It means that the universe has a structure that exists on two levels, the visible and the invisible, interpenetrating each other, connected through gravity, yet never interacting in any other way. It means that the beautiful galaxies we observe, the cosmic structures that inspire wonder and awe, exist as consequences of a far vaster and more fundamental structure that we cannot see. And it means that understanding the universe requires us to constantly think beyond what we can directly observe, to develop theories and models that explain the invisible alongside the visible, to read the universe's language through multiple means, not just through the light we can see, but through the gravity we can measure, the mathematical patterns we can discern, the logical inferences we can draw from careful observation. The universe's hidden architecture becomes apparent when we examine how galaxies cluster together, how they form groups and superclusters, how these larger structures arrange themselves across cosmic distances. When astronomers first began mapping the three-dimensional distribution of galaxies in space, they discovered something unexpected and beautiful. Galaxies weren't distributed randomly throughout space. Instead, they seemed to cluster along filaments, with vast empty regions between the filaments, what astronomers call voids. These voids are not completely empty. They contain some dark matter and the occasional galaxy, but they are far less densely populated than the filaments. The overall structure resembles a cosmic web, or perhaps a three-dimensional network of roads connecting cities, with the galaxies marking the cities and dark matter comprising both the roads and the vehicles traveling along them. This cosmic web structure is not something that emerged randomly from the early universe. Rather, it was predicted by theoretical models of cosmic structure formation, based on dark matter's gravitational pull. In the earliest moments after the Big Bang, the universe was nearly perfectly uniform, matter distributed with almost complete equality throughout space. But there were tiny ripples, infinitesimal variations in density from place to place. Dark matter, following gravity's patient and inexorable logic, amplified these tiny variations over billions of years. Where matter was slightly denser, gravity became slightly stronger, pulling in more matter, becoming stronger still, until vast filaments of dark matter had accumulated. Between these filaments, the matter remained sparse, creating the cosmic voids. Visible matter, falling into the gravitational wells created by dark matter, collected in similar patterns, forming galaxies along the dark matter filaments. This process, called cosmic structure formation, unfolded silently and invisibly over billions of years, with dark matter doing most of the work, dark matter creating the gravitational landscape upon which everything else was arranged. Visible matter, with its ability to radiate energy through light and heat, eventually formed stars and galaxies within this dark matter landscape. But without dark matter's gravitational architecture, without the invisible framework it provided, galaxies would never have formed at all. The visible universe, all the stars and galaxies and cosmic structures we observe, is built upon and supported by dark matter. This is not metaphorical, it is literal. The universe's structure, its organization, its beauty, these all depend fundamentally on dark matter's presence. Now imagine, if you will, observing the universe through a very strange instrument, one that could only see dark matter and not visible matter at all. What would you observe? You would see vast filaments of dark matter extending across billions of light years, intersecting and forming a cosmic web of extraordinary intricacy. You would see enormous clumps of dark matter where galaxy clusters exist. You would see the filaments and the voids. You would see the large-scale structure that shapes the universe. But you would see no galaxies, no stars, no planets, no light of any kind. You would perceive a universe that is elegant, organized, full of structure and meaning, yet completely dark. This is the dark matter universe, the invisible universe that surrounds us, the realm of gravity and mass that exists parallel to the visible universe of light and electromagnetic radiation. The two are intimately connected, One cannot exist without the other in the cosmos as we know it, yet they are fundamentally separate, perceivable through different means, interpretable through different frameworks. The gravitational lensing observations that astronomers use to map dark matter reveal this structure with increasing clarity. When light from distant galaxies passes through regions of space containing dark matter, it is bent, distorted, magnified. By carefully studying these distortions, astronomers can create maps showing where dark matter is concentrated. These lensing maps reveal filaments of dark matter, clumps of dark matter surrounding galaxy clusters, the overall cosmic web structure. And remarkably, the pattern of dark matter revealed by lensing observations matches perfectly with the pattern of visible galaxies. Wherever galaxies are clustered, dark matter is concentrated. Wherever galaxies are sparse, dark matter is less dense. The two, dark matter and visible matter, follow the same large-scale patterns, yet for different reasons. Visible matter clusters where dark matter's gravity pulls it, but it also forms stars and galaxies because of complex processes involving chemistry, cooling, star formation. Dark matter clusters where gravity pulls it and nowhere else. This brings us to one of the most important realizations about dark matter's role in the universe. Dark matter is democratic in a way that visible matter is not. Visible matter experiences pressure, experiences radiation, experiences electromagnetic forces, experiences the forces that govern chemistry and nuclear physics. These forces can push visible matter around, can cause it to cluster in some ways and spread out in others, can create complex structures and phenomena. But dark matter experiences only gravity. Gravity acts on all mass equally. It attracts everything. It is never repulsive on individual particle scales. It affects all particles with mass in the same way. Because of this, dark matter's behavior is, in a sense, simpler and more fundamental than visible matter's behavior. Dark matter simply accumulates where gravity pulls it most strongly, creating the cosmic web through pure gravitational dynamics. Visible matter falls into the gravitational wells created by dark matter, and there undergoes the complex processes that lead to star and galaxy formation. This is why dark matter is so important for understanding galaxy formation. Visible matter alone, without dark matter, would be unable to form galaxies. Here's why. In the early universe, shortly after the Big Bang, when dark matter and visible matter were still coupled together in the same fluid, both would have started to collapse under gravity toward overdense regions. But as visible matter collapses and heats up, it radiates energy in the form of light. This radiation carries energy away from the collapsing region, allowing the matter to continue cooling and collapsing. But there's a limit to how fast this can happen. Meanwhile, dark matter also collapses, but it doesn't radiate energy. It just keeps collapsing under gravity, growing more and more concentrated. The result is that dark matter collapses faster than visible matter, forming gravitational wells into which visible matter then falls. Dark matter is, in a sense, gravity's most efficient accumulator, the substance that most readily responds to gravity's pull and most quickly creates the gravitational structures that visible matter then inhabits. In the early universe, this difference in collapse rates had profound consequences. Dark matter filaments formed first, creating the gravitational architecture of the cosmos. Visible matter followed, falling into the dark matter's gravitational wells, collecting in regions of high dark matter density, cooling and eventually forming the first stars and galaxies. Without dark matter playing this foundational role, visible matter alone would have distributed itself more uniformly throughout space, and galaxy formation would have been much slower or perhaps impossible. The universe we observe, full of galaxies, full of structure, full of light, owes its very existence to dark matter's gravitational architecture. The visible cosmos is built upon dark matter's invisible foundation. If you're still contemplating this cosmic journey with us, if the immensity of this dark matter-built universe is beginning to settle into your awareness, we'd love to know what aspects of this hidden architecture fascinate you most. Is it the scale of it? Is it the elegance of the cosmic web? Is it the realization that galaxies are merely the visible ornaments on an invisible framework? Please share your thoughts and observations in the comments below. Your engagement helps us understand what aspects of these cosmic mysteries resonate most deeply with you, and it helps us craft future explorations that address the questions that captivate your imagination. As we move deeper into understanding this hidden architecture, consider a specific example: the Virgo supercluster, the vast collection of galaxy clusters that includes our own Milky Way and the Andromeda Galaxy. This supercluster is not randomly arranged. The thousands of galaxies within it are distributed in filaments and clumps, all following the underlying distribution of dark matter. Observations of the Virgo supercluster's structure, combined with gravitational lensing maps that reveal dark matter's location, show that the supercluster is organized around several massive filaments of dark matter. Galaxy clusters are concentrated along these filaments. Individual galaxies are arranged in patterns that reflect the dark matter's distribution. The visible structure that we can observe, the arrangement of galaxies we can photograph and catalogue, is simply the visible manifestation of an invisible dark matter structure that extends far beyond what our telescopes can see. This principle applies not just to the Virgo supercluster, but to the entire observable universe. Every galaxy cluster, every filament of galaxies, every large-scale structure that we observe is underlain by and shaped by dark matter. The universe's architecture is fundamentally a dark matter architecture, with visible matter, stars and galaxies and planets, arranged within it. When you look at photographs of the universe taken by the Hubble Space Telescope, when you see those magnificent structures of billions of galaxies arranged in cosmic patterns of extraordinary beauty, you're actually looking at the visible surfaces of dark matter structures. You're seeing the light that shines from visible matter embedded in the gravitational scaffolding of dark matter. The true universe, the full architecture, is far more vast and intricate than what any telescope can show us. To understand how dark matter shapes the universe, imagine building a model of a city. First, you construct the streets and roads. These represent dark matter filaments. Then, you place buildings at the intersections and along the roads. These represent galaxies and galaxy clusters. The buildings exist where they do because the street network guides their placement. Similarly, dark matter filaments form first, and galaxies accumulate along them because that's where gravity pulls them. The cosmic web is not just a pattern that galaxies happen to follow. It is a gravitational structure that determines where galaxies can form and exist. Dark matter, by not interacting with light, by responding only to gravity, creates a cosmic scaffold of profound geometric elegance. The universe is not a random collection of galaxies distributed haphazardly through space. It is an organized, structured cosmos whose organization is determined by dark matter's invisible but all-pervasive gravitational influence. One of the most beautiful aspects of this hidden architecture is that it operates on all scales. There are dark matter filaments extending across billions of light years, connecting distant galaxy clusters. There are dark matter halos surrounding individual galaxies extending far beyond the visible disk of the galaxy. There are dark matter structures within galaxy clusters, concentrating near the cluster's center. Even our own Milky Way galaxy is surrounded by an enormous dark matter halo, extending hundreds of thousands of light years from the galaxy's center, far beyond the visible stars. This halo is what causes the galaxy's rotation curve to remain relatively flat at large distances. The dark matter's gravity holds the outer stars in their orbits. Without this dark matter halo, the Milky Way wouldn't exist as we know it. The stars in the outer regions of the galaxy would have long ago flown off into space, and the galaxy would have dispersed into a diffuse halo of isolated stars. The Milky Way's beautiful spiral structure, the organized disk of stars that we call home, is held together by the invisible dark matter surrounding it. This realization that our own galaxy, the Milky Way, is embedded in an enormous dark matter halo should give us pause for contemplation. We live within this dark matter halo. Our solar system is immersed in it. Our bodies are constantly being passed through by dark matter particles. Dark matter is not something distant and abstract. It is, in the most literal sense, part of our cosmic neighborhood. The dark matter surrounding the Milky Way is not some exotic phenomenon occurring in distant regions of the universe. It is here, now, all around us. As you rest and contemplate this, you might reflect on the profound reality that you are not merely a resident of the Milky Way galaxy, but a resident of a dark matter halo, a structure of gravity and invisible mass that is far larger and more fundamental than the visible galaxy itself. The architecture of dark matter revealed through gravitational lensing and other observations, show structures of breathtaking complexity and beauty. Dark matter filaments are not simple, smooth threads, but rather delicate structures with branches and sub-branches, clumps and concentrations arranged in patterns that reflect the universe's fundamental physics. These patterns are not random, they follow laws of gravity and physics that operate throughout the cosmos. Theoretical models of structure formation, based on our understanding of gravity and the initial conditions of the universe shortly after the Big Bang, predict the patterns that dark matter should form. And when astronomers observe the actual distribution of dark matter through gravitational lensing, they find that observations match predictions with remarkable precision. This agreement between theory and observation is itself a profound testament to our understanding of dark matter and gravity. Consider the Fornax cluster, another nearby galaxy cluster, where gravitational lensing observations have mapped the dark matter distribution in exquisite detail. The maps reveal an intricate structure of dark matter, a main concentration at the cluster's center, surrounded by secondary concentrations and filaments extending outward. This structure is not arbitrary. It reflects the violent history of galaxy clusters, where smaller clusters have collided and merged over billions of years, combining their dark matter and galaxies into larger systems. Each merger leaves traces in the dark matter distribution, the remnants of older, smaller clusters still visible in the dark matter's structure. By studying these structures, astronomers can read the history of cosmic collisions and mergers, can understand how large structures built themselves up from smaller components, can trace the cosmic story written in dark matter's invisible but increasingly well-mapped architecture. As we contemplate the scale and complexity of dark matter's cosmic architecture, it becomes clear that we live in a universe far more intricate and profound than any previous generation could have imagined. Dark matter is not a minor component, not a small correction to our theories, not an oddity to be explained away. Dark matter is fundamental. Dark matter is primary. Dark matter creates the stage upon which the visible universe performs. Every galaxy, every star, every planet, every atom that makes up your body exists, because dark matter first created the gravitational structure that made their existence possible. The visible universe is in this sense a secondary phenomenon, beautiful and complex and worthy of study, but secondary to the dark matter universe that underlies and supports it. This perspective might seem to diminish the importance of visible matter, to suggest that stars and galaxies and planets are less fundamental than dark matter. But this would be a misunderstanding. Visible matter, though less abundant than dark matter, has properties and capabilities that dark matter lacks. Visible matter can interact with electromagnetic radiation, can form atoms and molecules, can undergo chemistry, can create life. Visible matter can produce light, can generate the photons that carry information across cosmic distances, can create the electromagnetic signals that make communication possible. In this sense, visible matter is more complex, more interactive, more capable than dark matter. Dark matter is fundamental and primary in terms of gravitational structure, but visible matter is primary in terms of complexity and capability. The universe needs both, dark matter to create structure, visible matter to populate that structure with complexity, light, and life. And so we find ourselves in a cosmos that operates on two levels. The dark matter universe provides the gravitational scaffolding, the invisible architecture, the fundamental structure. The visible matter universe provides the complexity, the light, the chemistry that makes stars, planets, and life possible. These two universes exist intertwined, each dependent on the other in ways both obvious and subtle. Dark matter could not create galaxies without visible matter to observe and study, and visible matter could not form galaxies without dark matter's gravitational wells to accumulate in. The two are locked together in a cosmic dance of mutual dependence, creating a universe far more beautiful and more profound than either could create alone. Now we venture into the realm of active exploration, into the laboratories and observatories where scientists work to understand dark matter's nature and properties. For decades, physicists and astronomers have known that dark matter exists, have mapped its distribution throughout the universe, have confirmed its presence through countless observations. But the fundamental question remains: what is dark matter made of? What are the actual particles that comprise this invisible substance? This question has driven scientific research and cosmic exploration, has motivated the construction of increasingly sophisticated instruments and experiments, and has brought humanity to the threshold of perhaps the greatest discovery in modern physics. The search for dark matter's nature is not a simple matter of building a better telescope and pointing it at dark matter to see what it's made of. Remember, dark matter doesn't interact with light, so no telescope can ever directly image dark matter particles or reveal their properties through electromagnetic radiation. Instead, scientists must employ more subtle and ingenious methods. They must infer dark matter's nature from its effects, from the way it behaves, from the traces it leaves in experiments designed with exquisite sensitivity. Some of these experiments search for dark matter particles passing through detectors on Earth. Others search for the rare interactions between dark matter and ordinary matter. Still others search for the products of dark matter, particle annihilation or decay. All of these approaches share a common philosophy. If dark matter particles exist, if they are present throughout the universe, then it should be possible to detect them directly through careful, sensitive experiments. One of the most promising approaches involves searching for weakly interacting massive particles, or WIMPs. WIMPs are hypothetical particles that have mass. They would be massive, at least in terms of particle physics, but interact very weakly with ordinary matter. A WIMP might occasionally collide with the nucleus of an atom, transferring a tiny amount of energy that could theoretically be detected by a sensitive detector. The challenge is that such collisions would be extraordinarily rare. If dark matter is as abundant as observations suggest, and if WIMPs interact as weakly as theorized, then a typical detector might need to observe billions of atoms for years before detecting a single WIMP collision. Yet scientists have built detectors sensitive enough to attempt exactly this. These detectors are typically located deep underground, shielded from cosmic rays that would otherwise create confusing signals that might mimic dark matter collisions. The Large Underground Xenon Detector, or LUX, was located a mile underground in an abandoned gold mine in South Dakota. LUX used ultra-pure liquid xenon to detect potential WIMP collisions. When a WIMP collides with a xenon nucleus, it would create a tiny flash of light, just a handful of photons, but enough to be detected by extremely sensitive light detectors surrounding the xenon. LUX ran for several years, accumulating data from billions upon billions of xenon atoms, searching patiently for the telltale signature of a WIMP collision. Though LUX did not definitively detect dark matter, the experiment set strict limits on where WIMPs could hide in terms of their properties and interaction strengths. Other experiments, including Xenon 1T in Italy and Super CDMS in Minnesota, employed similar strategies with similar sensitivity, all searching for the elusive WIMP signal. The beauty of these experiments from a scientific perspective is their elegance and patience. There is something profoundly moving about human dedication to solving mysteries. Scientists spend their careers designing detectors, running experiments, analyzing data, searching for signals that might not exist, might be infinitesimally rare, might require years of patient observation before revealing themselves. This is the nature of fundamental physics research, a patient, methodical search for truth, driven not by the promise of immediate results, but by the conviction that understanding the universe is worth the effort and the wait. As you contemplate this search happening right now, deep underground, in laboratories around the world, you might consider what this dedication says about humanity's commitment to understanding the cosmos we inhabit. The search for dark matter is not limited to looking for WIMPs, however. Another strong candidate is the axion, a hypothetical particle predicted by certain extensions of the standard model of particle physics. Unlike WIMPs, which are expected to be relatively heavy and rare, axions are expected to be extremely light and extremely numerous. If axions comprise dark matter, the universe would contain billions upon billions of axions in every cubic centimeter of space. An axion might occasionally convert into a photon, a particle of light, in the presence of a strong magnetic field. This conversion would allow axions to be detected indirectly, by looking for the distinctive photon signals that would result from axion to photon conversions in specially designed experiments. Several experiments are currently searching for axions using this principle. The Axion Dark Matter experiment, or ADMX, uses a large cylindrical cavity with a powerful magnetic field. If axions are indeed the dark matter, they should occasionally convert into microwave photons within this cavity. ADMX is designed to detect these microwave signals with extraordinary sensitivity, scanning slowly through different frequencies, searching patiently for the telltale signature of axion conversion. Like the WIMP searches, the axion searches are exercises in patient methodical observation in humanity's commitment to solving the universe's deepest mysteries. These experiments might run for years or even decades, scanning through wide ranges of possible axion parameters before finding a definitive signal, if axions indeed comprise dark matter. What's remarkable about these searches is that they represent human determination to solve a mystery that might not be solvable with currently available technology. Scientists don't know if WIMPs or axions actually exist. They don't know if dark matter particles are something entirely different from what current theories predict. Yet they proceed with experiments anyway, driven by the conviction that the search itself is valuable, that the attempt to understand the universe is worth the effort regardless of outcome. This represents a profound aspect of scientific endeavor, the willingness to pursue truth with patience and dedication, accepting that years of effort might yield negative results that are nonetheless valuable, because they constrain the possible nature of reality. The space-based searches for dark matter complement the Earth-based detector searches. Satellites and observatories in space are looking for indirect signatures of dark matter, for evidence that dark matter particles annihilate each other or decay, producing high-energy radiation that could be detected. The Fermi Gamma Ray Space Telescope, for example, looks for excess gamma-ray signals from galaxy centers and the galactic halo, where dark matter is expected to be most concentrated. If dark matter particles are annihilating each other in these regions, they would produce gamma rays that Fermi might detect. Similarly, the Alpha Magnetic Spectrometer aboard the International Space Station measures cosmic rays and looks for signatures that might indicate dark matter decay or annihilation. These space-based searches offer a different approach. Rather than waiting for dark matter to collide with a detector on Earth, they search for the radiation produced when dark matter particles interact with each other. The variety of search strategies, underground detectors looking for collisions, cavity experiments looking for axion conversions, space telescopes looking for annihilation signals, demonstrates the breadth of the scientific approach to solving the dark matter mystery. Scientists are not placing all their bets on one approach. Instead, they're exploring multiple avenues, using different techniques, casting a wide net in hopes of catching the elusive dark matter signal. This diversified approach reflects scientific wisdom, the recognition that the universe might surprise us, that our leading theories might be incomplete, that truth sometimes lies in unexpected places. The dark matter might turn out to be WIMPs, might be axions, might be something entirely different that no one has yet predicted. By pursuing multiple search strategies simultaneously, the scientific community maximizes the chances of making the discovery when it comes. As we contemplate this active search for dark matter, conducted by thousands of dedicated scientists in laboratories and observatories around the world, we might reflect on what this search reveals about human nature. We are driven by curiosity, by the desire to understand the universe, by the conviction that mysteries are meant to be solved. We are patient, methodical, willing to spend years pursuing leads that might prove fruitless. We are collaborative, sharing data and methods and insights across institutions and nations. We are humble, acknowledging the limits of our current understanding while working to expand those limits. The search for dark matter is not merely a technical endeavor, it is a profound expression of human aspiration to understand the cosmos we inhabit and our place within it. Every experiment running deep underground, every satellite scanning the sky for gamma rays, every physicist analyzing data in search of patterns and signals, all of these represent humanity's commitment to truth and understanding. If you have followed us this far into the search for dark matter, if you have contemplated the enormity of the mystery and the dedication of those seeking its solution, we invite you to share your thoughts. What aspects of this search fascinate you? Are you intrigued by the patience required for these experiments? Are you moved by the human dedication to understanding the universe? Are you curious about what dark matter might turn out to be? Please let us know in the comments. Your thoughts help us understand what aspects of scientific exploration resonate most deeply with our audience. And your engagement is part of the collective human conversation about our universe and our place within it. We're all, in a sense, part of this search, all participants in humanity's ongoing journey toward understanding the cosmos. The experiment searching for dark matter represent the cutting edge of physics, the frontier where known and unknown meet. They are places where extraordinary sensitivity is required, where the faintest signals might carry profound significance, where patience and precision are paramount. A single WIMP collision, if detected, would revolutionize physics and confirm what astronomers have long suspected: that dark matter is indeed composed of yet undiscovered particles, that the universe contains forms of matter completely different from ordinary atoms and nuclei. An axion signal, if found, would have similar implications and would suggest a particular extension of the standard model of particle physics that many theorists find elegant and compelling. Each negative result, while perhaps disappointing in the short term, constrains the possible properties of dark matter and guides future searches toward unexplored parameter space. The searches for dark matter are also remarkable for the international collaboration they represent. Scientists from institutions around the world, in the United States, Europe, Asia, and elsewhere, work together on these experiments, sharing data, contributing expertise, collaborating in the common pursuit of understanding. The Xenon collaboration, for example, includes researchers from dozens of institutions across multiple continents. ADMX has benefited from contributions from scientists across the globe. This international cooperation reflects the recognition that fundamental physics is a human endeavor, not limited by national borders or political boundaries. The cosmos is the common heritage of all humanity, and its mysteries are pursued by scientists from every nation and culture, working in concert toward truth and understanding. As we continue drifting through this contemplation of dark matter's nature and the searches underway to reveal it, consider what might be the implications of discovering dark matter's true identity. If scientists detect a WIMP or confirm an axion signal, what would this mean for physics, for cosmology, for humanity's understanding of the universe? It would mean that the universe contains entire categories of particles previously unknown to science. It would mean expanding the standard model of particle physics, the framework that has served physicists well for decades but which clearly remains incomplete. It would open new avenues for research, new questions to pursue, new mysteries to contemplate. And it would affirm that the universe is more complex, more subtle, more full of surprises than we had imagined. The discovery of dark matter's nature would not end the mystery of dark matter. It would transform the mystery into a foundation for new inquiries, new explorations, new adventures in understanding. End.